Okay, our speaker today is Professor Eli Waxman from Weizmann Institute. Eli is a well-known theoretical astrophysicist. His biggest achievements were predicting at least as far as I can see, predicting the flux of ultra-high energy neutrinos long before the ice cube, which actually measured them, was built and measured just the thing that was on the point of his pen many years ago, and also claiming that ultra-high energy cosmic rays are all coming from gamma ray bursts. On this one, we are still not sure, but maybe someday we will know. Okay, but today he will be in a different capacity. He will fly a satellite apparently soon. Okay, please.
Thanks, Andre. So I will be telling you today about the ULTRASAT, which is a very wide field of view ultraviolet satellite that we are building. The mission is led by us at the Weizmann Institute with the participation of, with the support of the Israeli Space Agency and participation of DESI in Germany and NASA, and I will say a few words about the roles of these different members of this collaboration. So the main goal of ULTRASAT is to study transients. Let me explain why we do this and what we achieve. So the study of transient astronomical events is becoming one of the main activities in astronomy. This is due to two main reasons. One is that many interesting open questions, and the other is that technological developments. So let me start with the open questions. So there are many transient sources that are highly interesting and want to understand, like the sources of gravitational waves that emerge from the mergers of binary neutron stars and black holes, the explosion of supernovae, the tidal destruction of stars by supermassive black holes, the descent of galaxies. So we are interested in understanding all these objects as astrophysicists. But their study is also expected to enable us to answer some questions which are of wider interest. For example, we believe that heavy elements which are produced by the rapid neutron star capture process beyond iron are produced by such binary mergers, but we don't have a proof of that. We don't understand how massive stars explode. Although Andrew told me that this is just being resolved now, maybe.
It's claimed to be.
Claimed to be, but this is still an open question. We want to understand how supermassive black holes affect the stellar environment. So studying these transient events will enable us to answer, we hope, all these open questions. Now, these questions are long-standing open questions. Why do we think that there's going to be a major change in the coming few years? This is mainly because technology now enables us to build telescopes with very wide fields of view. So there are wide field of view observatories being constructed in the optical, in the radio, X-ray and gamma ray, and also in other messengers. So we now have neutrino high energy material detectors, which are very wide field of view, and gravitational wave detectors, which are wide field of view. So the combination of these capabilities are promising to enable us to make significant progress. And the UV is missing from this list here. And the ULTRASAT is going to close this gap, being the first wide field UV transient survey. So the main advantages of key properties of ULTRASAT are its very wide field of view, 200 square degrees, and its UV sensitivity, which is about 10⁻³ photons per square centimeter per second. This combination of wide field of view and sensitivity enables us to monitor a volume of the universe for transients, which is hundreds of times bigger than anything available today. What you see here, this is the accessible volume to different surveys as a function of the wavelength at which the survey operates. The ULTRASAT is normalized here to 10. What you see here, these are existing transient surveys in the optical. You see that ULTRASAT is going to be about 100 times more sensitive than them. And this is the expected sensitivity of the Vera Rubin Observatory, or LSST, that will begin operation in 2024, and ULTRASAT will have a similar grasp in LSST.
Where is your ULTRASAT again?
Yeah, this one.
And if you go to right. But why is it important again to have, because above ULTRASAT there is also only X-rays, right?
You mean in shorter wavelengths?
Right.
X-rays and gamma rays.
And those will be a large gap or whatever.
Yeah, there will be some of
So
that.
the units of accessible universe volume, you indicate numbers there. What are
It's normalized to ULTRASAT. So this ULTRASAT is 10 in these units, and so all the others are normalized to that.
But I guess the question is, what is the absolute value?
This depends on the sources that you look for, right? How bright they are. So different.
That's why it doesn't make sense. You can't normalize the ULTRASAT without having an opinion of how bright a given source is in the different wavelengths, right? Supposing there are no sources, then in what volume does ULTRASAT see that you compare to Rubin? I think that was the source of Sure, question.
So there are two different things. It does make sense to normalize like this, independent of the luminosity of the sources, because it doesn't matter what the luminosity is, the relative volumes will be the same. There is an issue with this, what the spectrum is. Now, so this is made for 20,000 degrees Kelvin sources. So for hot transient sources.
So you're saying the sensitivity makes no difference in that plot. All that makes a difference in that plot is the angular size.
No, sensitivity does make a difference.
So
This is a
what
plot.
sense-
This
so
is a
what
plot.
sense-
This is a plot including sensitivity and field of view. So for all the different surveys, taking into account their field of view and sensitivity, we compared the volume that is available.
No,
for
but
them.
what does it mean to compare the UV sensitivity to the sensitivity? Well,
So if you have a 20,000 Kelvin source,
oh yeah.
you know
if
you know exactly how to compare them. So this plot is made for 20,000
So you're saying-
Kelvin.
Taking some specified temperature thermal source,
20,000 degrees Kelvin source.
and that's the one you're interested in. Okay.
This
that's-
is an example.
No, but that's how you did that plot.
This is this particular.
Okay.
So, in addition to the large volume that ULTRASAT will be sensitive to, it would have several other advantages. First of all, it would monitor a new window in wavelengths, which is the UV, which is not accessible from the ground. Second, being in space, it would enable us to obtain a continuous cadence, observing the same sources from minutes to months, the minutes cadence of observations. It will be in a geo-orbit, so it will provide real-time alerts on any transient that it detects to the time and worldwide community. And it would be very agile, so it will be able to suit any point on the sky in minutes time scale to follow up on transients detected by other surveys. Now, with increasing the accessible volume of the universe by a couple of orders of magnitude compared to anything that is accessible today, implies that you would have impact on a wide range of open questions. I will discuss briefly our top two key science goals. And the first is the mergers of neutron stars. So for those of you who are not in this field, what are we interested in? So tight binaries, tight meaning separations less than 3 million kilometers roughly, would merge on a Hubble time by emitting gravitational waves. And as you know, the first detection of such a merger was in 2016. LIGO detected the merger. What?
2050. Or do you mean for neutron stars?
No, the neutron stars was 2017. This was 2016. So this was the merger of a binary of two 30 solar mass black holes. Now we are interested in the mergers of binaries in which one of the components is a neutron star. These are more interesting in a sense because in such a merger, some part of the neutron star material is torn up and expelled at relativistic speed, and this expelled material is highly radioactive because of the heavy elements produced by the large neutron fraction in the ejecta. And so this radioactive, rapidly expanding ejecta emits hot radiation that is possible to observe. And as I mentioned, we believe that this is the location in the universe where the heavy arc process elements are produced. So the detection of electromagnetic emission following gravitational wave detection of binary merger would be one of the major goals of astronomy in the coming decade. And identifying the electromagnetic emission would enable us to answer the question of which heavy elements were produced in such mergers. It would enable us to study the properties of nuclear matter because the properties of the neutron star affect the ejected material. And finally, if we can actually localize these events and measure the redshifts of the galaxies, it will provide us with a direct measure of the Hubble constant, independent of the distance ladders. What are the advantages of ULTRASAT in this game? So, at late 2026, we expect with the upgrade of gravitational wave detector networks that they would provide one detection per month of such a merger out to a distance of about 300 megaparsecs with an error box of about 100 square degrees on the sky. They're not very accurate in localizing the direction. Now, ULTRASAT will be able to slew a minute's timescales to any point on the sky away from the sun. Thanks to its very wide field of view, it will cover the entire gravitational wave error box in a single image. And if our estimates of the UV luminosities are correct, it would detect these events to beyond 300 megaparsecs. So it would detect these events rapidly and localize them rapidly, and will provide a UV light curve starting from minutes after the event to days or months after the explosion. So,
and would not some optical telescope be able to do the same?
I'll answer this in the next slide.
Okay.
But this sets our timeline. So the 05 of LIGO is set to begin at late 2026, and we want to be in space early 2026 to be ready for that. Now, we have so far one binary neutron star event that was detected, followed up, and for which optical and UV emission was detected. Okay, this is this event of 1708-17. Now, the electromagnetic emission was detected here about 12 hours after the gravitational wave detection. And the reason was that narrow field optical telescopes that went to look for this transient had to go over all the galaxies in the error box until they found the source. And this took 12 hours. Now, there are several issues here. One, when the horizon of gravitational wave detection increases to 300 megaparsecs, it would be impossible to do this game. Play this game, but there would be many thousands of galaxies in the error box. The ULTRASAT, as we said, will cover the entire error box in a single image. And the other is that this event, although it was detected 12 hours after the burst, it was still extremely hot. It was hotter than 10,000 degrees. We have only a lower limit on the temperature, and it was very bright in the UV, which implies that ULTRASAT would have detected it to well beyond 300 megaparsecs. On the other hand, this event was also detected in gamma rays, but only because it was extremely close, about 40 megaparsecs from us. It was a very lucky event, and it wouldn't have been detected had it been at a distance of 60 megaparsecs. Okay. And finally, although this event has been very well monitored and measured, we still don't know which elements have been produced. So we know that radioactive unstable process elements have been produced because we see the radioactive emission heating up the ejecta. But we don't know whether heavy elements up to germanium were produced or maybe up to gold. And early UV measurements of the light years would enable us to discriminate between these different models.
Maybe you said this, but if there's thousands of galaxies that could potentially be the source, will you be able to distinguish? I guess you need regular resolution for that.
Yeah, we would detect the electromagnetic emission, so our localization would be very good. We don't have this problem. The problem is not to, when you detect the electromagnetic signal, you know exactly what the source is. The problem is if you need to look at all the galaxies, then it's not to detect
I think the question is about the your angular resolution.
I'll get to you see the resolution. The second goal of ULTRASAT is to study
But
the...
sorry, Eli, because you mentioned this gold or whatever, so is it true that gold is only produced in neutron star mergers or not?
We don't know.
Oh, we don't even know.
We don't know. We want to know if it's produced there.
But haven't they detected gold in some lines of supernovas or something?
I don't know of gold lines in supernova.
But if you say we don't know, it means they haven't.
I'm not aware of such a measurement of gold lines and gamma ray lines from supernova. I don't think that this exists.
We would know if they had it, because it's so controversial that you need another source.
I think that it's possible because it's not possible to detect gamma ray lines from supernova. I know away from our galaxies. I'm sure that it.
But just as a matter of fact, is it? You are saying nobody knows how gold is produced? Yes. Okay. If you say so.
Well, we know it's produced by this process, but we don't know where it is produced.
Like, for example, we know that carbon is produced in whatever, in stars.
Right. But you cannot produce in stars beyond iron, right?
Okay.
Because it's the most most stable element. You need to produce the others by some neutron capture reactions.
Okay.
And the rapid process is difficult to, the neutron environment that you need for the rapid process is difficult to produce. It probably doesn't happen in supernovae.
And you can only make gold by this rapid process.
Well, no, you can make it, but not with the abundance that we see it. If you want to expand the abundances that we see, you need the rapid process.
Okay.
Okay. Second open question that ULTRASAT will hopefully help answering is the depth of massive stars. So, as I said, the supernova mechanism is still not understood, and one of the ways to make progress is to identify which type of progenitor star explodes which type of supernova. Now, this has been done for a handful of events by looking at pre-explosion images of galaxies that were taken by the Hubble Space Telescope and identifying the star that disappeared after the explosion. Now, this is a very difficult game to play, and it's very difficult to extend this to a large number of supernova. And an alternative is to detect the very early UV emission of the explosion. This enables us to determine the size of the exploding star, its surface composition, and also its mass loss history prior to explosion. So we have some theoretical predictions for the UV emission, and these are observations of such explosion in the UV. You see that the error bars are very big, so this is serendipitous detections by galaxies. What you see here is that our theoretical expectations are sort of roughly correct, and you can see also that UV measurements would enable you to distinguish between different types of progenitors. ULTRASAT will detect hundreds of supernovae per year at an age less than a day. What you see here in this histogram is the number of ULTRASAT detection as compared, for example, for the existing ZTF or the upcoming Rubin or LSST observatories. And this is the number of events that ULTRASAT will detect in less than an hour. while the other surveys will not be able to detect such events at all. Now, the importance of detecting a large number of supernovae is that we need to detect the rarer types. If we want to do a complete mapping of progenitor type to supernova type, we need to detect also the rarer type of supernovae. Most of the events are going to be the explosions of big red supergiants, but detecting only those will not help us. We want to detect the blue supergiant and the ultra-Ray explosions, and ULTRASAT is the only instrument that will enable us to do this. Okay, so these are two of the science goals that we will be addressing. As I mentioned, increasing the accessible volume to transient surveys by a factor of a few hundred is going to make a big impact on many different, on the study of many different astrophysical objects. I've talked about two sources from this table, but ULTRASAT would affect significantly contribute to the study of all these events. Tidal disruption events by supermassive black holes, so to detect more than 100 per year. And this will be the first time that we will be able to systematically study these events. Monitoring many thousands of active galactic nuclei with continuous scales from minutes to months in the UV band. Cataclysmic variables, our liner stars. Okay, there would be many interesting astrophysical applications to the ULTRASAT measurements, and I want to touch one of these additional science goals, just because this is not a high energy astrophysics type goal, and this is to do with planet habitability. So, as you know, there are large surveys searching for Earth-like planets around young solar analogs, these M-dwarf stars. Now, these M-dwarfs are very active in the UV, and the UV activity has several implications. First, strong UV activity may inhibit life formation. On the other hand, UV activity may be important for the initial prebiotic chemistry. Finally, strong UV activity can produce molecules in the atmospheres of these planets that are considered as biomarkers, like ozone. So you might be seeing ozone, and it would not be the result of life, but of UV activity. Now, this is why understanding the UV activity of these M-dwarfs is important.
I'm sorry, why ozone is the marker of life?
It's one possible marker of life, not necessarily.
Oh, because it is oxygen,
Yeah.
simply, okay. Not ozone particularly, just oxygen.
Yeah. So now this UV activity is not well known, and ULTRASAT will enable us to actually accurately characterize it. ULTRASAT will monitor some hundreds of thousands of M-dwarfs, and it would map the UV activity. It would enable us to determine which type of M-star has which type of UV activity, and therefore which type of star is most likely to host a habitable planet. And if you have, if you want to point out to expensive spectroscopic capabilities to study some atmospheres of some planets, we will tell you which types of planets are worth your investment. Okay. The word about the mission profile. So at the beginning of the mission, we would spend a few hours a day for 6 months to produce an all-sky map. This would be a reference map. It would be 7 times deeper than the UV map that was produced by Galax. And it will be our reference map for detecting transients. When we look later at the sky and we search for some transient, this would be our reference. Now, most of the time, ULTRASAT will be staring either near the north ecliptic or near the south ecliptic galactic poles. These are the directions where we would minimize both the extinction of the galaxy and the zodiacal light emission from the solar system. And occasionally, we would follow up transients detected by other surveys like gravitational wave detectors. we will be able to slew to any point in the sky, as I said, in units time scale. There's essentially no limit to the number of these target of opportunities that you can perform. There's one limitation, which some directions we don't have sun, so we have a negative power balance, and we cannot allow more than 75 of these negative power target of opportunities. If these events are randomly distributed over the sky, about 1/3 of the events would be this negative power. Okay, so it's not a real limitation. I hope that we will have 200 neutron star merger triggers to follow during the mission.
You mean the solar panels are rigidly fixed? So what is it?
Yeah, yeah.
So what,
It's loose to some position. At some angle, we will get negative power consumption.
is there a way to just have them rotate on their own?
There is a way. It takes. It increases the mass, the cost, first of the satellite. So, okay, so this is a good introduction to the satellite. A few words about the satellite. At the center is the telescope. Okay. The focal plane array, the telescope is being produced by ELOP, which is an Israeli company, according to the design that was led by Gil Belami at Weizmann. The focal plane array is the contribution of our DESI partners. The sensors, the special UV sensors that you see here, which I'll say a few words about, have already been produced by Tower, which is another Israeli company. And the telescope would be integrated into the satellite, which is being constructed by the Israeli space industries. You can see here the dimensions and the mass. Most of the mass is fuel. The NASA's contribution to the mission is launch. And the launch would be to a GTO orbit, so geotransfer orbit. This is a very elliptic orbit that reaches a geostationary distance, 36,000 kilometers at one end, but very close to the Earth on the other end. And in order to circularize this orbit, you need a lot of fuel, and this is most of the mass of the satellite. The launch is planned for the beginning of 2026, as I mentioned. In terms of reliability, the minimum reliability requirement is 3.5 years in orbit. Satellites usually live much longer, so we will carry fuel for 6 years of operation at the geostationary orbit. You need to carry a little bit of fuel in order to evacuate your geostationary position. You go up 300 kilometers to what's called the graveyard orbit, and you need a little bit of fuel to maintain your orbit while you are at the geoslot. So once you really get below this fuel required for this maneuver to the graveyard orbit, you will need to evacuate the position. Okay, some brief description of the technology and the challenges there. So this is a partial list of the technical requirements that we need to meet in order to achieve the very wide field of view and the UV sensitivity. And so we have limits on the optics. The PSF needs to be better than 15 arc-second. Out of band separation needs to be better than about 10⁻3. Quantum efficiency of the detectors. This is a crucial point. Needs to be larger than 60% in the UV. This is something that was not possible to do 10 years ago. So this was one of the major challenges. The other challenge was to keep this low point spread function across this huge field of view. We have a huge buffer.
What is the dark current?
Yeah. So the dark current, this is the this is the flux of electrons that come out from a pixel that is not illuminated. It's just noise. Okay. So this needs to be less than 0.03 electrons per second per pixel. And this implies that we would cool the detector to 200 Kelvin, passive cooling, to meet this requirement. Yeah, so this is another challenging requirement from the sensor, but the real tough thing was this 60% QE.
Which is defined how exactly? What's the definition of quantum efficiency?
How many electron reads you get per photon hit? So how many?
60% means
60% of the photons would produce an electron in our readout. Okay, now we have a huge buffer. Most of the telescope that you've seen is a buffer. Okay, so all this thing here. And this is because we need to suppress stray light by 11 orders of magnitude. Okay, to avoid stray light from the Earth and the Moon, increasing our background. And another interesting thing is that in geo orbit there are lots of high energy electrons, and these electrons will penetrate our lenses and produce Cherenkov light that is blue and will produce a dominant background. So the buffer is not only screening stray light, it is also a bit thick to absorb high energy electrons from prevent them from hitting the lenses.
But electrons are coming from all directions, no?
Yeah, so that's why the limit is reducing them by a factor of 6. Those that come directly at the lens, we cannot avoid. Okay, so a word about the focal plane array. The key part here is this backside illuminated CMOS detectors. We would be using 4 tiles, and each of them would be independent, so completely independent. So if one tile somehow malfunctions, the other 3 continue with no problem. The challenge to get high quantum efficiency here is met by 2 things. One is a special surface coating with a high dielectric coefficient material. This prevents the accumulation of charge when the UV photons hit the detector, which is one of the major problems of getting high quantum efficiency detectors in the UV. And the second is a special anti-reflection coating that prevents strong reflection of the UV photons. Okay, and a special design of the electronics to be radiation hard and so on. So these are the specs of the sensors. It's roughly 10 by 10 centimeter, the 4 tiles, about 100 megapixels, more than 60% quantum efficiency in the UV, and so on. Now, this was one of our key challenges, as I mentioned, but this is behind us. The sensors have been produced, and the performance has been measured. You see here one of these tiles. We of course produce many more than 4. We build 4 flight models and many more tiles.
Whose idea it was to send up this large field of view ultraviolet satellite?
I was developing this idea from 2010.
And who told you to develop it?
No one told me to develop it.
Really? No, I'm just curious. I would have never thought up such a thing.
So actually, the head of the Israeli Space Agency at that time, whom I knew from some other reasons, came to my office one day and told me, "Can we do something with the Israeli capabilities in space?" I said, "Okay, let me."
So you did get some external influence.
Yes, and then I said, "Okay, let's think about this." And Shri Kulkarni was visiting at Weizmann at the time. Sometimes I said, "Okay, let's think about this together," and we formed this group of scientists, Weizmann and Platek. It involved some engineers from the IAI and Elbit, and it took us about 2.5 years to convince ourselves that we can do this.
Okay.
And 5 more years to get the funding. Okay, so the sensors have already been built. These are quantum efficiency measurements for different anti-reflection coatings. They all meet the 60% average in our waveband. and we've chosen to go with this T2. And if you want to read more details, there are some detailed papers describing this the satellite, the telescope. Okay, as I mentioned, there's a big baffle. The light comes from this direction. It enters the telescope through this double corrector lens, reflected by the mirror, then hits this double field flattening array, and then the detector sits here, looking backward into the mirror. Each of these lenses and these lenses is a tandem made of two different materials, calcium fluoride and fused silica. And the reason is that the wavelength dependent refraction index, wavelength dependence of the refraction index in the UV is very strong in different materials, and it's very difficult to build a very wide field of view telescope with a very good PSF. So using these two materials allows us to correct for much of these effects. And in addition, just next to the detector here, we have a sapphire coated filter that will enable us to reject out-of-band light, infrared and optical light from reaching our sensor. Now the performance of the coatings of the lens and of the mirrors and of the filter have already been measured. So what you see here are measurements. So this is the total throughput. This is in band between 230 to 90 nanometers. This is out of band. So we meet the requirements for out of band suppression and for in band throughput. And with this, now this is the model. The telescope has not been built yet. It is being built now. But we can model now our PSF. This is the wavelength dependent PSF as a function of distance in angles from the center of the detector. And this is the effective PSF across the field of view. Okay, so the effective PSF is about 8 second average, average. And this enables us to determine that we will meet our sensitivity requirements, 22.5 magnitudes. This is determines 3 photons per centimeter per second. And this is the budget of our noise. So most of our noise is going to be from the zodiacal light from the solar system. The second major component is the Cherenkov light that is produced by relativistic electrons hitting the mirrors. And the rest is small. These are pictures to show you that the telescope is actually being built. This is a new build. So you see, this is actually happening as we speak. This is the polishing of the mirror. This takes many weeks. You can sit here for a few weeks. Watch this.
So what is the size of this mirror?
The mirror is 0.5 meter, and the clear aperture is 33 centimeters.
So this is the back mirror, not the one that you said.
It's a back mirror. Yeah. So in the center, at the entrance, we have a lens, a double lens.
And then you make sense.
It goes to the mirror. It goes to another double lens, which is a field flattener, which flattens the field of view, and then it goes to there.
Do you know the coding for this UV reflection? What kind of coding?
So there are several oxides of hafnium, titanium, silicon. Okay, the mission status. Our program is so far on track for launch at the beginning of 26. Industries are working. We believe that all the risks have been identified and are well mitigated by our project. Maybe I should mention one of the key challenges is contamination. So organic molecules absorb heavily in the UV. And if we use some glues in the satellite, when you go to space, you can have this degassing from all these organic materials. If they stick to the lenses, they would kill us. So the contamination requirements, of the choice of materials and all the construction of the satellite need to be produced under very strict contamination regulations to avoid this. So I think we identified all these problems. We're on track, as I said, meeting the launch date beginning of 26. And the total approximate cost of this mission is about $110 million, including launch, which is fairly affordable. I still want to say cheap. Fairly affordable for this type of mission.
How much of that is the launch?
I don't know exactly. NASA not exactly on this, but I probably can.
Who's launching? Who's launching the satellite?
NASA. So there would be. I will say a few words about the collaboration.
And Hubble had its own like worries with the mirror, so that was subcontracted. So how? Suppose that you made sure that this mirror came out right.
Yes. So we would measure the performance of the optics and the detectors on ground, both at ELOP that produces the telescope, and then later at IAI that does the integration. So I think that there's no way we would get to space with performance not meeting the requirements. Maybe I should something that you don't mention. There is also a focus mechanism for this is a very fast telescope, so there is a focus mechanism in the satellite in case that we are a bit defocused after launch. We'll be able to correct for that. It's another risk, but I think that is also one mitigated. All the data from ULTRASAT would be continuously transmitted to the ground. We have a 5 megabit link. All the data processing would be done on ground, nothing in space. The Science Operations Center would be at the Weizmann Institute. This is where all the data would come through. This is where transients would be identified. This is where the notifications would be distributed from to the world. And this is where we would command the satellite to slew to follow up transients detected by other facilities. I would like to say one word about supporting activity that we have at Weizmann. So one of the important things after detecting a transient and measuring its UV light curve is to follow it up with other wavelengths instruments. We are building, we means Sagi Ben Ami, Elan Ofik, and Avishai Galiam, an observatory in Israel, in the desert, that would do one of the major things that it would do would be follow up in optical infrared and spectroscopy for ULTRASAT targets. The important thing about being in Israel, among others, is that you see this blue gap here, is that observatories in other places of the world have this gap in longitudes that is not covered, and an observatory in Israel is uniquely suited to cover this gap, so this will enable us a rapid follow-up of events at any point on this flight. Just say one word about this observatory. So the idea behind this observatory is to use a large number of small aperture telescopes that would be combined with fiber optics to give you an effective big telescope. So you can either do a small field of view, very big telescope like 1.5 meter, or you can do a very wide field of view, small telescope. And the same for the spectroscopy. So this is one of the facilities that will enable us to do photometry and spectroscopy, a follow-up of ULTRASAT transients. One word about the collaboration. The alerts of ULTRASAT will be, of course, communicated to everyone in real time. The rest of the data will be proprietary for about 12 months. Scientists participating in the ULTRASAT working groups would have real-time access to all the data. There are 13 working groups focusing on different lines of the table that I've shown you. Most of the Israeli astronomers are members of these working groups already. In return to the NASA launch contribution, there will be 8 US PIs that will be able to join the project. James Rhodes from Goddard is the NASA project scientist for ULTRASAT, and a call from NASA for US PIs to join the project and receive funding for their activity is already out. Okay, so the deadline is March 31st, if you are interested. Our DAISY partners will receive free PI participation in the working groups, and our big competitor, the Vera Rubin Observatory, we have finalized an agreement with Vera Rubin, through which Israeli astronomers will receive real-time access to Rubin data in return for 6 additional US PIs joining the ULTRASAT working groups. Okay, so just some time to summarize. ULTRASAT will make a revolution in our ability to study transient events for several reasons. To firstly grasp the size, the volume of the universe that ULTRASAT will cover will be several hundred times bigger than anything available today and comparable to that of LSST. Second, it will provide, for the first time, observations in the UV. And being in space, it will do this with continuous minutes to months cadence, which is not possible to do on the ground. It will provide real-time alerts within minutes to the entire world community, and it would have a very strong target of opportunity capability, being able to shoot any point in the sky in minutes time scale. These are promising for making major progress on a wide range of open questions, some of which I've mentioned: gravitational wave sources, supernovae, variable flare stars, AGNs, tidal disruption events, and so on. We will be doing all this in a fairly affordable cost. And as I mentioned, the NASA call is out for your scientists that want to join. Proposals are due by March 31st.
So what exactly is groundbreaking here? Which ground will you break? So you will observe.
Seems that I failed in this talk.
No, seriously. I mean, if you are to fantasize, so to speak, what do you like? Okay, so you will see, instead of 1 neutron star merger, you will see 100 neutron star mergers.
So I think that.
Or maybe you will see something that you don't know about, or whatever.
Of course, there could always be some serendipitous discoveries that we do not expect because we have not explored this part of space.
And this perhaps is in fact the main hope, no? If you just see what you expect, would you consider yourself unlucky or not?
No, I think if we are able to measure 10, 20 neutron star merger afterglows, this would be a huge thing. And no one else would be able to do it. If we would be able to map the explosions of some several hundred supernovae to the progenitors, this is also going to be huge. So I think even if we do only this, I will be very happy. Yes. And if we do other things, of course.
How long will it stay up, this satellite?
So we plan for 6 years. I hope that we will meet this.
Well, the TVA, tidal disruption events, you said that 100 a year.
Yeah.
Does it expect?
This. This is unlike, okay, I think supernova, we know the rate best.
Okay, that's why.
We have some measurements, we have a theory, it's roughly fits, so I think we know the rate. Neutron star mergers, okay, roughly, we have one event detected, we have some estimates, gamma rays and so on, but so I guess a 10 per year is a good number, but it could be a 3 and it could be 30, I don't know.
TDA is difficult to
TDE, at least 100, because the models for TDEs are all over the place. So one thing that we will do is to systematically map the TDE population. So I think it's at least 100 per year.
Anybody else? Then let's thank Eli again.